Today we'll start bivariate data analysis. This is chapter 5, and the learning outcomes are you will be able to know the cross tabulation, scatter diagram, and you can perform simple correlation analysis. Okay, you will be able to conduct linear regression analysis, and then once you get the results of your model, you would be able to know how to measure the goodness of it, of the model, and significance of the regression coefficient. Also, we will discuss about the unit root test, and we will discuss the bivariate causality test and Engel-Granger co-integration test. So first topic is cross tabulation. So it's very simple. You have studied simple frequency table. Okay, so in a simple frequency table, we have just one variable, and we report the frequencies of the data. Here we have two variables. Okay, more than two variables. Okay, but because today we are discussing about bivariate data analysis, so we will focus only on two variables. Analysis with two variables. So cross tabulation is a joint frequency distribution of two or more variables. Then I will show you. Now in this case, if we are performing some statistical test, so then this would be called as contingency table. Okay. Otherwise, a simple cross tabulation. Here is the cross tabulation, and this is the hypothetical example of gender age. Now here we have gender variable. Here we have age variable. Now in gender we have classification, male and female. Okay. In age we have different age groups. Okay. The first age group is 20 to 25, then 26 to 30, 31 to 35, 36 to 40, and over 40. These are different age groups. Now if I want to discuss about this variable, age and gender, this data, so this is 28. So this means there are 28 male whose age is between 31 to 35 years. Okay. And there are two females like this here, this one. There are two females whose age is between 36 to 40. Now this is total. There are total 40 male, there are 40 female, and then there are total 80 observations. Okay. And for here, suppose in 20 to 25, there are no female, they are just male, two male, and total are two. So this is the total of each column. Okay. This is the total of each row. So in this way, we plot the cross tabulation, and then we learn something from the data. Then in bivariate data analysis, this is very popular. We perform correlation analysis. Okay, and correlation is basically a degree of relationship between two or more variables. It could be linear or it could be non-linear. Okay, we will discuss about linear correlation. Okay, it could be curvilinear. Okay. Now, so correlation is said to be linear if the ratio of change is constant, and if the ratio of change is not constant, then correlation would be non-linear. Now, correlation between two variables could be positive, it could be negative, or it could be zero. Okay. If the two variables are moving in the same direction, then we say there is a positive relationship. Okay, correlation would be positive. And if the two variables are moving in opposite direction, then we have negative correlation. And if the two variables are changing with no connection to each other, then it means correlation is 0. Okay, like price and quantity supply. What do you expect? It will be a positive correlation or negative correlation?
Sir, positive correlation.
Yes, positive correlation. Okay, like, and price and quantity demanded,
Negative correlation, sir.
negative correlation. Okay, income and saving,
Sir, positive correlation.
positive correlation. Okay, production of wheat in Pakistan and rainfall in USA.
Sir, no correlation.
Yes, then there will be no correlation. Okay. Okay, good. So you can just think about many variables. Now, for your own data also, you have to calculate the correlation between different variables. Okay. Now, to learn about the correlation, we have two methods. Okay, we have a scatter diagram. Through scatter diagram, we can know about the nature of relationship between two variables and also the extent of relationship. And then we have correlation coefficient. Okay, we calculate a number, and then on the basis of that number, value and sign, we can say about the nature and extent of correlation. So in a scatter diagram, we plot the paired values of two variables on a graph paper and keep them scattered. Okay, we don't join them. Okay, we just, so if we have two variables x and y, we just take the paired values of x and y and we plot them on a graph paper, and then we look at how that graph looks like. So on the basis of that plot, we can say whether the relationship is positive or negative or zero, or there is strong positive or there is strong negative, or there is a perfect positive or there is perfect negative. So we can say something. This is the scatter plot. We have x variable here, y variable here. Okay. Now you can see that here, these are the paired values of x and y. Now this is positive correlation because both variables are moving in the same direction. Okay. So this is the positive correlation, and if the scatter plot, they are very close to each other, so it would be strong. Otherwise, it would be a weak correlation. Same as here, we have negative correlation, okay, because the two variables are moving in opposite directions. Here, we have no correlation, so they are changing with no connection to each other. Okay, so we have zero correlation. Then we have correlation coefficient. Okay, so scatter diagram will just give you an idea about the nature and extent of relationship. But the problem with the scatter diagram is we cannot come up with the same conclusion by different scholars. Okay, so maybe you are saying this is not strong, someone else is saying it is strong or very strong. So you here, maybe you say this is zero correlation, but maybe it is a very weak correlation. So for this, we have to calculate correlation coefficient. Okay, and this was introduced by Carl Pearson. This is also known as the Pearson correlation coefficient. So this is a precise quantitative measurement of the relationship. Now for this parameter, it can take value between -1 to +1. So if the value of correlation coefficient is -1, so we say that there is a perfect negative correlation between two variables. And if the value of correlation coefficient is +1, so we'll say there is perfect positive correlation. And then the value is in between -1 and +1. So if it is 0, then it means there is no correlation. Now, if the value is closer to +1, so there is a strong positive correlation. If it is closer to -1, then there is a strong negative correlation. And if the value is closer to 0, so this means there is a weak correlation. Then the problem with correlation is we cannot study the cause and effect relationship. Okay, so we cannot say if x is changing by some value, by what amount y will change. Okay, so in a correlation analysis, there is no dependent or independent variable. Okay, we just study the relationship. But in linear regression analysis, we can study the cause and effect relationship. Okay, so we can also say by how much one variable will change due to change in another variable. This we cannot say in correlation analysis. Okay, so in 1886, Galton, introduced this concept of regression. Okay, and he studied the height of parent and the height of children. Okay, so he found there is a tendency for all tall parents to have tall children, and for short parents to have short children. Okay, and he further discovered that the average height of the children tends to regress or move towards the average height in the population. Okay, this was very important. And after this, there were many studies, and this is now a very standard analysis, regression analysis, and we are using it very frequently, and it is very helpful for forecasting also. Okay, in this regression analysis, we have dependent variable and independent variable. So if we have dependent variable and one independent variable, so this would be a simple regression analysis. And if we have more than one independent variable, then it would be multiple regression analysis. So mostly in our research studies, we perform multiple regression analysis. Okay, but the starting point is where we have to study simple regression analysis so that we could understand the analysis, and then the extension is the multiple regression analysis. So this is, so I'm giving you example of saving and income. So suppose y is saving and x is income variable. Okay, now this is a simple regression model. This is in parametric form. Okay, so we have two variables now. That's why it is simple regression model. So x variable, y variable. So saving depends on income. Okay. Now saving, which is y in the regression model, is also called dependent variable. And we also call it explain variable or response variable, predicted variable or regression. Okay. And this x is called independent variable. It is also called explanatory variable, control variable, predictor variable, or regressor. Okay. So in this, this is model. We want to see if x changes by some amount, then by how much y will change. Okay. And also for a particular value of x, what would be the value of y? So it means prediction. Our forecasting is also possible once you get the values of these parameters. Now in mathematics, we study exact relationship. Okay? If it is mathematics, we have y equal to alpha naught plus alpha 1 xi. Okay, that's all. That is exact relationship. But in econometrics, we study inexact relationship. We also introduce error term. Okay, because we know that saving not only depends on income. There are many other variables on which saving depends. So this error term will take care of all those variables that are not included in this model as explanatory variable or independent variable. So this is the advantage of using a regression model. Okay, so we are taking care of other variable also. Okay. Now this is population regression model. Okay. Now if we get the data for the entire population on y and x, then we estimate the values of alpha naught and alpha 1. But in reality, it is difficult to get the data of the entire population. So we get the sample. Okay, so that's why we estimate the sample. Okay, so sample observations are used, and this is the estimated regression model. And these are the parameters that are used to get the estimated values from sample observation. And now this is the estimator of population parameter alpha naught. This is the alpha 1 hat is the estimator of population parameter alpha 1. Now what we want that this alpha naught should be close to alpha naught hat. Okay, alpha 1 hat should be close to alpha 1. Okay, so sample from sample, whatever the parameters that we are getting, it should be very close to population parameter. So if they are very close, and then error term will be close to 0. Now how to get these estimated parameters values? So we have least square method. Okay, ordinary least square method. So this method is very popular, so we have to minimize the errors. Okay, and one method is to minimize the simply error. But the problem is, if we are minimizing the error, maybe there are some negative error and positive error. Okay, because the difference between this y and y hat is the error. Now the error could be positive. Okay, if y is more than y hat, the error could be negative if y is less than y hat. So we have positive error, we have negative error. So if we minimize the sum of error, then it could be 0. Sum of error could be 0, but there are still positive or negative errors. Another method is we have to take the square of the error. So then negative value will be cancelled out, and then if we minimize the errors, that would be a better method. So ordinary least square methods, they in that method we minimize the sum of squared error. Okay, and then with that minimization process we get these estimators. Okay, alpha 1 hat, this is the formula, alpha naught hat, we have another that is in the appendix. Okay, so alpha 1 hat we will get by this, or we can get by this. So here. Okay. And now we have EViews software or Excel or some other SPSS, so we can get the values of these estimators. Okay, alpha naught hat or alpha 1 hat. Okay. And when we are using the ordinary least square methods, OLS method, which is very popular, so these estimators are blue. They are best linear unbiased estimator, and an estimator is unbiased if its expected value is equal to its true value. So OLS estimator is also efficient because they have a smaller variance. compared to other estimators. Okay, and the OLS estimators is consistent because this estimated value approaches to the true value when population size becomes very large. So this is basically the Gauss-Markov theorem, uh, which states that when all assumptions of least square methods hold, the OLS estimators are blue. They are best linear unbiased estimator. So that's why we use OLS method, because the estimators are best linear and unbiased. And these are the assumptions of the OLS method. Okay, and if any one of the assumptions violated, then it creates problem, and then we have some econometric problem. Okay, and then we try to fix those problems. Okay, first assumption is that regression model is linear in parameters, so it would be linear in parameters, and the values of explanatory variable are fixed in repeated samples. The mean or expected value of random variable, which is the UI error term, is 0. Okay, and the variance of the error term is same for all observation. So if it is not same, then we have a problem. Again, econometric problem, heteroscedasticity problem would be there. Okay, and then we are assuming that error terms are uncorrelated with each other. If the error terms are correlated, then we have autocorrelation problem. Okay, which you have studied in your econometric course. And there is zero covariance between the error term and the explanatory variable xi. Okay, and the number of explanatory variables should be less than the number of observations. Okay, and the values of x in a given sample must not be all same. Okay, so they should not be same, and the specification of the regression model is correct. If the specification of the regression model is not correct, so we have misspecification error. Okay, and this assumption is that relationship between explanatory variable is not perfect. Okay, so if there is a very strong relationship between explanatory variables, then we have multicollinearity problem again. So all these assumptions are for the OLS methods. This is the result which we got for our suppose saving model. Now this is 20.25, 0.15. Suppose you use OLS method and you got this result. Now this shows that the minimum average value of Y, which is saving, is $20.25. So irrespective of income level, so income is 0, then saving would be $20.25. So 0.15, this is the marginal propensity to save. Okay, and a value of 0.15 shows there is a positive effect of income on saving. So this sign, if it is negative, so it means there is a negative effect of X on Y. If it is positive, this means, so we look at the sign here also. Okay, and we also look at the sign here. And this shows 0.15, that $1 change in income will change saving by $0.15. So if income increases by $1, saving will increase by 0.15. So if income increases by $100, so this model says that saving will increase by $15. And also we can predict the value of saving by putting a specific value of income. So if income is $1,000, what would be the saving? So just put 1,000 here. Yes.
Sir, $150.
No. Don't forget this. You will put 1,000 here. If income is $1,000, so you will put 1,000 here. 1,000 multiplied by 0.15 is 150, and also plus this one, no? 20.25. 150 plus 20.25. 170 point.
25.
Yes. Okay. Clear?
Yes, sir.
Okay. Then we have to check the goodness of it. How good fit is our model. So to measure the goodness of fit of the model, we use the coefficient of determination, okay, which is the ratio of explain sum of square to total sum of square. Okay. So total sum of square measure the total variation of actual y about their mean, k, and explain sum of square measure the variation of estimated y about their mean, and residual sum of square RSS, unexplained or residual sum of square measure the variation of y about regression line. So this is okay. This is the mean value of dependent variable y. This is our regression line. Okay, so this all these point on this line would be y hat. Okay, so and this is the actual y. So actual y is this, mean y is this, and estimated y is this. Okay, so this is average saving, this is estimated saving, this is actual saving. Now for this income level, you can see that this is the actual saving, this is the estimated saving, so this is the error, no? Y minus y hat, this is the error term, no? And this is due to residual, and then this is the error due to regression. Okay, this is average, this is the estimated value, okay, and this is the total. Okay, now this is the regression results of saving model. If you use the time series data file and run this for the sample 1982 to 2015, okay, and there is a variable in the data file DSAV, which is domestic saving, and this is GDP RB, this is GDP rupees billion. So if you pick these two variables from that data file, and if you estimate using OLS method with EViews, then this would be the EViews output. Okay, I suggest you to replicate this result by using the time series data file. Okay, so you will get this result. Okay, now you can see that, but you have to be careful that you have to use this sample. Okay, 1982 to 2015, then you will get this result. If you are using a different sample, then you will not get this result. Now looking to this regression results, we can say that here GDP rupees billion, here 0.26. So marginal propensity to consume is marginal propensity to save is 0.268, like this. Okay, and this is the t-value, this is the standard error, okay, and this is the probability. Now this variable, income variable, has a significant positive effect on domestic saving, because the probability value is 0.000. So if the probability value is 0.05, are less, so we will reject the null hypothesis. The null hypothesis is that there is no effect of income on domestic saving. Alternative hypothesis is that there is some effect of income on saving. So in this case, we reject the null hypothesis that there is no effect of income on saving because of this, the probability value of t statistics. Now, this is the R square. So in this case, we will look at the R square because here we have just one variable. So if there are more than one variable, explanatory variable in the model, then we will look at to the adjusted R square. Okay. Now 0.947, it means 0.95. So 95% variation in saving is explained by income. Okay, this is the case. Okay, so 95% variation in saving is explained by income. So it means 5% variation in domestic saving is explained by some other variables that are not included in this model as explanatory variable. Okay, now here then we have this F statistic, which is this is the probability of F statistics. So this means the model is significant overall. So we look at the overall significance of the model with the F statistics. Okay. Then there are some others. Durbin Watson we will discuss later on. Okay. So this way we get the result of the simple regression model. And this is the plot for the actual saving and estimated saving, okay, fitted saving and the residual. So this is the red line is the actual saving, okay, and this green line is the fitted saving and this is the residual. So we want to fit, so sometime you will get a very good fit model. So if your R square value is 0.99, so then they will overlap, okay, the actual and fitted, and the error would be close to 0. So I will stop here. Okay.